Okay, so we're going to go ahead and continue on with Chapter 9. And Chapter 9 is about what we call significance tests. And so we're going to keep working with these idea of sampling distributions and all that, and kind of look at another way of figuring out information instead of using a confidence interval. So we have this problem where a basketball player claims to make 80% of the free throws he attempts. You have seen him play basketball before and you don't believe him. So you ask him to shoot some free throws. Suppose he shoots 50 free throws and makes 32 of those free throws. Does that mean his claim is true, or that he just had a bad streak and his claim is false? So we've got to analyze a couple things first. What is his sample proportion? Well, if he made 32 shots out of 50, his sample proportion would be the 32 over 50, which is really 0.64, which is pretty low compared to his claim of 80%. So what can we conclude? Well, if you're an 80% free throw shooter, you don't always make 80% of your free throws. In fact, it's going to vary and it's going to average out right about 80%. So how do we determine the likelihood or the probability that he had a bad streak? Well, we can actually perform a simulation to find out. So what we did is we used Fathom software to create a sampling distribution, or to simulate 400 sets of shooting 50 shots, assuming that the person is truly an 80% free throw shooter. So we can look at that variation and how that distribution comes out. Now the dot plot is actually on your piece of paper. And again, this is kind of like a sampling distribution, not a full sampling distribution, but it's giving us an idea of what it would look like. So here's our distribution, 400 dots on this graph right here, all centered around that 0.8, assuming that he's an 80% free throw shooter. So he would make less, he would make more, but all right around that 80%. So now the question here is, how many of the 400 sets of shots were at our sample proportion? So he shot 32 out of 50, which was 0.64. And so when we look over here, 0.64 is right here. So we have three values that are 0.6 or lower. 3 out of 400, which means it's pretty unlikely. I mean, it's possible, but it's very unlikely that we would get a proportion that small. In fact, the probability is 0.0075, which is less than a 1% chance. Now, because it's less than a 1% chance that if they're truly an 80% free throw shooter, that they would shoot that low or have that low of a shooting percentage, then we can say that this is strong evidence, because it's saying that the probability of shooting that low of a percentage is so small that it's very unlikely that it could truly happen. So what is the probability he only made 32 shots out of 50 just by chance? Well, again, that 0.0075. So what we're doing is we're taking a claim of 80% and we're looking at this distribution here, and we're looking at, well, if this is true, what's the probability of getting this result? And that's what we're doing each time. We're going to take a look at, if this is true, what's the probability of getting that result? And then we're going to test that against this idea of, is it likely or is it unlikely? And then make a statement about our decision. Was the claim true? Was the claim not true? So please make sure you understand why the evidence is convincing. There's two possible explanations. Either the player is correct, and by very, very bad luck, very low percentage, he shot that badly, or they were wrong. The population proportion is actually less than 0.8, so the sample result is not unlikely outcome. And so we play these probabilities against each other in this chapter. So what we're going to do is a significance test. It's a formal procedure for comparing observed data, so our information from our sample, with a claim. So we're going to compare our sample information with a claim, and we're going to try and figure out what the truth is. We express the results of a significance test in terms of a probability that measures how well the data and the claim agree. So just as a little rundown, our significance tests are always looking at a population. We use the sample data to help us out, but we're really looking at what's true about the population. We're always going to ask ourselves if the sample data gives good evidence against a claim. And we're always thinking about this in terms of probability. If we took many random samples and the claim were true, what's the probability we would get a result like this? And the basic idea that we're looking at here is an outcome that would rarely happen if a claim were true is good evidence that the claim is not true. So like our previous problem, this is good evidence that the claim is not true because it's so unlikely to happen that our claim is probably not true. Okay, so when we're working with significance tests, we have two different hypotheses. We have what we call a null hypothesis, and that's a statement of no difference. So in our last problem, it could be what a person claims to be true, or it could be that it's just kind of the status quo, nothing changes. And our null hypothesis always looks like this H little o, or little zero. And zero just means that there is zero difference or no difference in it. Then we have an alternative hypothesis. Our alternative hypothesis is a claim that we hope or that we suspect is true instead of the null hypothesis. Now we have two different types of alternative hypotheses. There is a one-sided alternative hypothesis and a two-sided alternative hypothesis. A one-sided alternative hypothesis will claim that the actual parameter is less than the value in the null hypothesis, or it's greater than the value in the null hypothesis. So it'll look something like this. A two-sided alternative hypothesis will claim that the actual parameter is not the original value in the null hypothesis. So we use a not, and we typically do a two-sided alternative hypothesis if we don't suspect that it's greater than or less than. If we have a feeling that it's greater than, then our alternative hypothesis would be greater than. If we suspect that it's lower than, then we use the lower than. If we just aren't sure, then we use the not or the not equal to. So sample problem. Mike is an avid golfer who would like to improve his play. A friend suggests getting new clubs and lets Mike try out his 7-iron. Based on years of experience, Mike has established that the mean distance that balls travel when hit with his old 7-iron is 175 yards with a standard deviation of 15 yards. He is hoping that this new club will make his shots with the 7-iron more consistent, which is less spread. So more consistent means we're closer together to that mean value. So he goes to the driving range and hits 50 shots with the new 7-iron. What's the appropriate null hypothesis? Well, null hypothesis is no difference. So we start with null hypothesis is, and we're measuring standard deviation. So the null hypothesis is the standard deviation would be exactly the same as it used to be. So the same standard deviation before would be 15 yards. Now we're hoping that with this new 7-iron, we're going to be more consistent, which is less spread. So our alternative hypothesis is that standard deviation is actually going to get smaller because we're going to have less spread. So we suspect that it's less than 15 yards. And that's what we're going to test. We're going to test these two hypotheses. And every time we do a significance test, we should have a null and an alternative hypothesis. So something that you should know is that our null hypothesis will always have an equal sign. Always. We're always going to assume that it is a certain value. Now, our alternative hypothesis, this is where we use the symbols less than, greater than, or not equal to. And that will always happen. So as you're writing these and looking at multiple choice questions, it's something to keep in mind. Our null hypothesis should always be an equal to. So we're going to practice writing some of these hypotheses. So VitaBlend, a new brand of vitamins, claims in a radio spot that people who take VitaBlend vitamins wake up refreshed and ready for a new day within 5 minutes. So they're claiming that it happens within 5 minutes of their alarm sounding. Vitablend's internal research department conducts a test to support the claim heard on the radio. So null hypothesis would be that there's no difference. So that this is not actually changing the average wake up, get ready time. So our mean time should be about 5 minutes. Now they're claiming, or they're hoping, that their vitamins will actually help make it less than or within 5 minutes. So these are our two hypotheses. They're going to test to see, is it really or is it not within 5 minutes? And it seems like you'd want to say for the null hypothesis that this is greater than, but you don't, because we can only say equal to, so we stop at that limit, that 5 minute limit. If it's greater than, that's fine, we'll find that out in the test, but what we really want to know, is it less than? So that's what we're going to be testing. Okay, next one. The school principal is not pleased with the first semester exam scores of the first 2 period U.S. history classes. The mean test score for both classes was 72. He believes that the students' final exam score average will increase because the 2 teachers will teach the second semester by combining the classes and using a team teaching approach. So null hypothesis would mean that there is no difference. So my null hypothesis is there's no difference in the average score, so we'll assume the average score is still 72. The alternative hypothesis, what he hopes to have happen, is that those scores are going to get higher. So he believes the scores average will increase, so we want them to go higher than that 72. Okay, heading into the election, Jack needs 50% of the vote or higher to win. Jack is feeling pretty confident that he will win the election. Is his confidence warranted? So null hypothesis, we're using that border value. So we're talking about percentages, so we're going to go proportion is 0.5. And he's hoping that he's going to win. So he's hoping that he's going to have more than half the vote. Okay. A nationally known gardener claims to get 25% more blooms on a rose bush during the summer season. The bush must be fed his specially formulated water-based plant food for the first 5 weeks of spring. Last summer, Gemma's rose garden had a mean of 34 blooms on each bush. This summer, Gemma will feed her rose bushes the water-based plant food and test the nationally known gardener's claim. So we're assuming, for our null hypothesis, that there's going to be no difference. So we're going to have still a mean of 34 blooms, but we're going to test to see, is it really true that we'll end up with more blooms? And so it seems like you would want to use this 25% in there, but we can't, because we may get more blooms than the original 34. And so it's actually kind of working. It may not actually end up being 25%, but it may be more blooms. So we test with our current average, which is our no difference, and then we test to see if it's going to be higher. Remembering that this is always equals, and this one's our inequality. So a note about hypotheses. The alternative hypothesis should express the hopes or suspicions we have before, this is really important, we see the data. We always make those hypotheses before we actually collect data. It is cheating to look at the data first and then say, oh, well, this looks like greater than, so I'm going to make my hypothesis greater than. That's cheating. It doesn't work. And if it gets found out, your whole credibility is out the window and you'll never do research again. Hypotheses always refer to a population, not a sample. I said that already, but it's never too early to point that out. And if you're ever unsure, use that two-sided alternative hypothesis. Okay, so now we're going to go ahead and move on to talking about p-values. P-values are really just probability values. And it's the probability that measures the strength of the evidence. So again, what's the probability of this occurring if HO is true? So it's the strength of evidence against the null hypothesis is called the p-value. The smaller your p-value, the stronger your evidence against the null hypothesis. The p-value is known as a conditional probability. What's the probability of getting my alternative hypothesis value given the null hypothesis is true? So that's what we're doing. We're creating this distribution based on our null hypothesis value, and we're checking out what's the probability of getting this HA value. HA and higher. Or what's the probability of getting our sample value and lower. So it's really a conditional probability that we're looking at based on the idea that we're assuming HO is true, and we're looking what's the likelihood of getting the sample that we got. So now we have something called a significance level, also known as alpha in the Greek letters. To determine what p-value is considered small, which means that our conclusion is we reject our null hypothesis, or large, which means that we can't reject our null hypothesis, we fail to reject, we compare it to what we call a significance level, also known as alpha. Our significance level requires evidence against HO to be so strong that would it happen less than alpha % of the time. So if my alpha is 0.05, then it would mean that it would have to happen less than 5% of the time. So less than 5% chance of that happening given our null hypothesis is true. When our p-value is less than our alpha or our significance level, we say the result is statistically significant, meaning it's so unlikely that that could happen by chance that our claim is probably untrue. And so that's when we reject the claim or the null hypothesis. Significant does not mean important. It just means it's not likely to happen by chance. Now this is something that pops up with multiple choice questions, because it really depends on the context of what's happening to determine if it's important. This just means that statistically it's not going to happen by chance. If you're going to draw a conclusion based on statistical significance, your significance level should be determined before the data is produced. Now, significance levels should typically range from 0.1 to 0.001. Depending on what you're working with, you can go lower or higher in that range. So if it's not all that important, 0.1 is fine. If you're doing significance tests on medicines and stuff that affects people's lives and stuff like that, we go to a really low significance level because we want a very, very low chance of that happening by chance. Now, in the court of law, courts will accept a 0.05 or lower. So 0.1 doesn't work in court, but a 0.05 or lower. Now, if you're ever in doubt, or if a problem does not specifically state what significance level you use, you can go ahead and go default to that 0.05 because that is accepted in the court of law. So once you have went ahead and determined your significance level, you calculate all your stuff, you compare your probability to your significance level, then we come to statistical significance. So we draw a conclusion. Now we only have two conclusions. We can reject our null hypothesis. That means that our p-value is less than our significance level, or we can fail to reject our null hypothesis, which does not guarantee that HO is true, but it just says that we don't have enough evidence to say that HO is not true. And that happens when our p-value is greater than our significance level. And typically we don't write that our p-value is greater than our significance level. We say our p-value is not less than our significance level. And so that way we don't have to sit there and remember, oh, which direction does our sign go? It's always less than. And then when it's not less than, that tells us that we failed to reject. We failed that inequality. Now, something I do need to point out is never accept HO. You will lose credit on an AP exam. That is a different type of testing all together, we won't really have evidence that HO is true. We just won't have enough evidence to say HO is false. So we're always looking to try and make HA true. But again, we don't say that anything's true because based on probabilities, we really don't know the truth. We're just based on our evidence. We have enough evidence to reject, or we don't have enough evidence to reject, so we fail to reject. So in our previous beginning problem, in the free throw shooter example, the estimated p-value is 0.0075. That is strong evidence against the null hypothesis that the proportion of making that the sample proportion should be 0.8. So it makes 80% of our free throws. For that reason, our conclusion would be to reject HO in favor of the alternative hypothesis that likely they make less than 80% of their free throws. It appears the virtual player makes fewer than 80% of the free throws. So sample question, when Mike was testing a new 7-iron, the hypotheses were standard deviation is 15. He's hoping with the new one that the standard deviation will be less than 15. So we do the problem, and then all of a sudden we get this p-value of 0.002. What does that mean? Well, it means that if the true standard deviation is 15, meaning if this is true, then the probability of getting a result of 10.9 is 0.002, or 0.2% chance. So now that we know that, we're going to test our probability. We're going to see, is it less than our significance level? Which it is. So what should we do? We should reject our null hypothesis, which means we have convincing evidence that the new standard deviation is less than 15. So we have evidence that this is true with the new 7-iron. So we have evidence that that 7-iron is making his shots more consistent. Okay, so for another problem, not already written out for you, for his second semester project in AP Stats, Zenon decided to investigate if students at a school prefer name brand potato chips to generic potato chips. So that's what we're comparing. He randomly selected 50 students and had each try both types of chips in random order. Overall, 34 of 50 students preferred name brand chips. Zenon performed a significance test using the following hypothesis. So he's assuming that it's equal, that people really can't tell the difference. So half the people like name brand, half like generic, no big difference between the two. But he suspects that more people really like the name brand potato chips. So he suspects more than half the people will like it. So he got a p-value of 0.0055. What conclusion would you make at each of the significance levels? So we test 0.0055. Is that less than 0.01? Yes, it is less than. So we reject the null hypothesis, which means, and so usually you sit there and state, okay, this is less than our significance level, which means we reject HO, and now you tell me what that means in context. So we have convincing evidence. See a pattern here, right? So we have convincing evidence that this is true, that the proportion is really greater than 0.5. Well, what does that mean? That more people prefer name brand potato chips to generic potato chips. Okay, now our next one, we use a different significance level. So 0.0055 is that less than 0.001. If you have a hard time telling, is 5 and that spot less than 1? Well, it's not less than 1, which means we fail to reject. Which means we're going to state the same thing up here, but we do not have convincing evidence. And to save yourselves time, but the exact same thing from down there. So we do not have convincing evidence that more people prefer name brand potato chips to generic potato chips. And that's it. So that's really trying to give us the bones of what we're going to do this chapter. We haven't even talked about how do you calculate that p-value, how do you do all the mathematical calculations and our conditions and stuff. We're just talking about the main idea behind our statistical test.